back. So in the previous course we have seen that the largest inductance, which is 1 Henry, had the lowest current flow in the circuit, while the circuit with the lowest inductance had the highest current flow. But what happens if the inductances are the same and the frequency of each AC power source is different? Well, let's find out. In this circuit we have 3 inductors, each with equal inductances, but this time the frequency of each circuit is different. What is happening here? Well, as you can see, inductors are able to pass lower frequencies more easily than higher ones because they oppose changes in current, and low frequency AC has more gradual changes, giving the inductor a chance to adjust. So the higher frequency of the bottom circuit results in a lower current. This is very interesting. If you change the inductance of the inductor, the current will change. If you change the frequency of the AC power source, the current changes again. There must be something that we don't know yet, and it makes all these things confusing. Well, the culprit of all these is nothing else but the impedance of the inductor. Even though there's a dedicated course just for impedances, I want to cover this here because this is very important for you to understand. But before explaining what impedance is, I want to show you something else. So these circuits show the response of a capacitor and an inductor when driven by alternating current. Current, which is yellow, and voltage, which is green, across the capacitor are shown in this scope. And note that current leads voltage when current peaks. The capacitor is just starting to be charged and voltage is 0. When voltage across the capacitor peaks, the current stops and begins to flow in the opposite direction. On the other hand, when AC passes an inductor, the current lags voltage. So when current starts to flow, the inductor resists it and voltage across the inductor is at maximum. As the cycle progresses, the inductor voltage goes to 0, allowing current to reach its peak value. A component is said to be reactive if it tries to resist a change in voltage or current in a circuit. The amount of resistance to the change is called reactance. So in order to resist a change in current or voltage, the component resisting must be able to store at least part of the energy applied. And the components capable of doing this are the capacitor, which is storing energy in the form of voltage, and the inductor, which is storing energy in the form of current. So in AC circuits, because the existence of reactive components, the voltage and current may not reach the same amplitude peaks at the same time, and they generally have a difference in timing. This timing difference is called phase shift, and it is measured in angular degrees. The point here is that when AC current is passing through a reactive element, whether it's capacitor or inductor, there will be a phase shift between voltage and current. When AC is passing a capacitor, the phase shift will be 90 degrees with current leading the voltage, and when AC is passing an inductor, the phase shift is also 90 degrees, but we can also say minus 90 degrees, where voltage is leading the current. Now let's get back where we left off, and we mentioned impedance, right? Impedance and resistance are similar ideas. Both represent how a component opposes or fights against the flow of current. When you say impedance in electricity, it is often used to describe as the measure of the opposition to an alternating current. It is basically resistance, but the concept is extended to AC circuits. Impedance is much more complicated than resistance, taking into consideration that it relates to AC. Resistance will only have to deal with non-shifting phases of voltage and current, which makes it simple. The same thing cannot be said of impedance, as it is determined by another value which is based on phase shifts aside from resistance. That extra aspect is the reactance. Reactance, which is either inductive or capacitive, is a circuit element's opposition to an alternating current. And knowing the reactance in addition to the resistance, one will be able to determine the impedance. This is to say that when one has to determine impedance, they will require an overall or a more extensive figure of the circuit. Both resistance and impedance are expressed in unit ohms. Mathematically, however, they are denoted differently. Impedance is often denoted with symbol Z, while resistance is often in R. Many people, including engineers and electronic enthusiasts, use the terms loosely, so they often use the terms interchangeably, especially in forms where instead of the more appropriate term resistance, they will use impedance. For instance, simple circuits practically without reactance are still referred with the term impedance. Nevertheless, technically speaking, it is still correct. It is always assumed that impedance is just another word for resistance. Strictly, it should be understood that the effect of resistance is constant regardless of the frequency. On the other hand, mixing the effects of capacitance and inductance will always result in impedance. So it basically means that the impedance varies with the frequency of the signal passing through the reactive element, which can be either capacitor or inductor. As you can see here, the impedance is defined as the combination of resistance and reactance. This chapter, as I said, is aimed to understand inductors in the first place, and going deep into mathematics regarding impedance and reactance would go beyond the scope of this lecture, and of this chapter actually. As I said, there will be a dedicated course where we will revise impedance and reactances again, so take this as a little introduction. Now, as a summary, we have learned that impedance is the measure of opposition to an alternating current, while resistance usually refers to direct current. Resistance is simple, while impedance will consider reactance in addition to resistance to determine it. Resistance is pure ohmic impedance, and the impedance is denoted by Z, while resistance is denoted by R. And last but not least, impedance may often take into consideration the overall circuit, while resistance may not.